Welcome to the latest edition of the I&I podcast. My name is Dan Aspel, I'm the communications manager here. Today I'm sitting down with Professor Martin Buhmann from Justus Liebig University near Gießen in Germany. Now, Martin, you recently gave a talk at I&I about the Mathematikum Centre. You are one of the directors there, is that right?
Yes, it is indeed a fairly new concept of presenting mathematics to the general public, which is nowadays called outreach for mathematics. Its purpose is to show the public how enjoyable mathematics is, what questions arise in mathematics, and to some extent how they are solved.
And the reason why I thought it'd be great for us to sit down and chat, although there are many that I could have chosen, is because of the motto of Mathematicum, which came up in your talk. And would you mind telling us what that is?
Of course. It is called hands on, minds on.
Which in German is?
Actually, we keep that in English.
Oh, really?
We do have a German concept,
Yeah.
which is Mathe macht glücklich, which means maths makes you happy.
Very true. Yeah.
But coming back to the hands-on, minds-on, that is the idea that you learn also how to solve profound questions like in mathematics, not only by looking at paperwork, books on a screen, but doing things with your hands. Many of our experiments, in fact almost all, are not using a computer, but they're using puzzles, experiments to solve or to understand mathematical problems by thinking about it, certainly, but also doing things with your hands. And that turns out to be, not only for children, but in particular for children, a particularly useful and lasting method.
And how have you found ways of measuring that, for example? What is it that you notice in the audiences at Mathematicum that makes this physical approach seem very successful?
The main point is we observe that people are enjoying themselves. And in the first moment, you could think mathematics is a dry and difficult subject, and people may not enjoy looking at this, they may run away. And we see both of it, that people enjoy themselves, singles, in families, large groups of children, for instance, in school classes, and we simply observe that people stay. They like it, they enjoy it, they stay the whole day, and do the experiments, and that is an enormous positive reaction, which we see without asking for questionnaires or anything like that. It's simply we observe how the people come. We also notice that people come, they come again, they solve problems, and we also, of course, talk with the teachers who bring school classes into the Mathematikum.
And as you mentioned in your talk, it's not just the fact that you're interacting with things with your hands, but they're very colourful for the most part, and designed with tactility in mind, perhaps, and they are very much the focus of the room. So there's a big physical draw to these puzzles, which is perhaps the opposite of what a lot of school children might think of when they think of maths. They think of a black and white textbook and a pen and paper. So is that something that's missing from the way that maths is taught in some styles around the world, do you think? Let's
say the way we do it, concentrating on particular problems which people do with their hands, is filling a gap. It's not replacing the mathematics that is taught, certainly in very good ways, in the school, but it's filling a gap to explain in a basic idea how mathematics works, what the problems are. So it is not a replacement for looking at books, but it certainly is a different approach. And the idea is to explain not only how mathematics works, but what it is for. This is something which is perhaps lacking in school. And many children, many adults ask, what is mathematics for? They will not ask a question like that if they learn biology or chemistry, but in mathematics that's not always so clear. We also show that in the Mathematikum at the same time as we show the mathematical principle how to solve problems.
I believe that's even a problem when it comes to non-school related activities. For example, funding for mathematics, higher research in mathematics. You often get the question of, well, what's the application? And as you say, biology, chemistry, you can see perhaps medical applications and other such fields which are very easy to sell to the public. But that itself, I suppose, is just a result of these attitudes which perhaps are gained at an early age. So do you think what do you think is the most meaningful thing that can be learned from what is happening at Mathematicum and the successes which you've found?
The meaningful thing is that people understand and enjoy mathematics, and then they carry on doing things which are mathematics related. And the applications you were talking about, like for instance medical applications, things to be done in hospital or in industry, apply in the same way to mathematics, but it's not so obvious. And once people see that mathematics is an important part of our lives, and that they do see this in the Mathematikum, they will also see later on that it is important to understand mathematics, and it was important for them to learn mathematics at school.
So in the description to this podcast, I'll put a link, obviously, to Mathematicum, and people can see for themselves pictures of the centre. But paint, if you will, for us a picture of the kind of puzzles which you have and the kind of form that they take, ones that perhaps have proven the most popular.
Very popular is, for instance, the one that shows you the meaning of so-called minimal surfaces. You notice if you create a big bubble out of soap, it will acquire a certain form. You can do the same if you stand in an experiment, which is a little bit like a shower. You stand in the middle, and then you pull up a soap film about you, which you would expect at the first moment to go up like a cylinder, but it actually has a form, getting close, popular to your an hourglass to your body. This, of course, people tremendously enjoy.
Yeah, you're standing inside a giant bubble.
Indeed, and you see literally millions of photos of people of themselves and others on the internet, and you can immediately explain that this has to do a lot with physics, so a form of surfaces which minimize energy that is needed to keep the surface together. Some people know, for instance, the roofs of the stadium of the Olympics in Munich in 1972, and the roofs have this form. They're not just straight, but they form this kind of holes in between, and that's called a minimal surface. That's one of the most popular experiments.
So was that designed, that stadium, from an aesthetic point of view or from a practical point of view?
Both at the same time.
Wonderful.
Often architects will tell you, there's a famous Bauhaus movement that was in Germany, that form follows function. You optimize the physics, for instance, or the energy that is needed to maintain a building, to build it, to heat it. If you do this at the same time, you create a building that has a beautiful form.
Yeah, so in this case, you've got quite a wondrous experience of people coming and standing inside a bubble that's being formed around them at the Mathematicum Centre. It's an easy way to get someone's attention, isn't it? So do you think that that's what has been lacking in most people's appreciation of maths, perhaps until this point? With most other sciences, you can feel yourself immersed in it somehow, can't you? Whereas maths, it requires that little extra step to capture the imagination, perhaps? Precisely.
There you are literally immersed in the soap bubble, and there are many things which have very profound mathematical principles. We, in fact, do not explain this principle in detail. We could if we wanted to, but the idea is people get immersed in the first simplified form of a mathematical problem that can be very profound, and they understand this idea very quickly. And then, if they want, they can carry on, going more into detail. If it's with children, they can ask a teacher. We have a bookshop, they can go into further detail. We have staff who can explain things, but they have sort of this first touch.
It's softly, isn't it?
It's softly, but the mathematicians behind it who create these things, my colleague Albrecht Beutelsbacher in particular, try to do with some success that these experiments are really well thought of. They look simple, but they explain mathematics principles in a profound way.
Yeah, one of the phrases which you used in your talk a few times was that they were non-trivial.
Exactly.
So beyond seeing the appreciation of form and physics, as you've described with the bubbles, there are actually some famous puzzles which you have given shape to.
Oh, indeed,
right.
yes,
Yeah.
indeed. There are even unsolved mathematical problems, where the so-called Goldbach conjecture, which is very simple to explain. It's typical of some of the hardest problems in mathematics. Many of them are still conjectures, have not been established. They're easy to formulate for everybody to understand, but extremely hard to prove. The Goldbach conjecture says very simply that for every even number, that is a number divisible by 2, there are 2 prime numbers, which have other than 1 in themselves, no divisor. There are 2 prime numbers that sum up to this even number. Now, this is something which everybody can understand. It's very easy to formulate. But it turns out up to this day, the mathematicians have been unable to prove it. And that's, in a way, a little bit what is behind the Mathematikum. There are things in mathematics which are very difficult, but actually, if you think about it, the ideas or the questions are reasonably simple to explain to the public. And that's what we try to do.
So how do you give physical form to that particular conjecture?
We have a kind of a rope that you can turn, which has all the numbers up to 100 on them, and you can turn them in the way that you form every number between 2 and 200 as a sum of 2 other numbers between those. And then you can check on this rope, we have marked the primes in red, the others are black, and then you can form one of these even numbers you like, and then you can check along the rope that there are actually 2 primes summing up to this number.
Yeah.
And one thing we hope, and we are reasonably optimistic that this happens, that people who've done this once, they enjoy it, and they will maybe someday, when the Goldbach conjecture has been proved, and certainly in the newspaper, remember, I've seen this maybe 2 weeks ago, we don't know when it's going to be solved, or 20 years ago, we saw this in the Mathematikum, this was this interesting question, now it's been solved.
Yeah, how fascinating. That's such a great way of capturing imagination, as we've said. And there was one other point I remember from your talk where you were talking about the travelling salesman problem, which probably has a more a better title than that. But you have made a map of Germany, have you not, with Mathematikum or Gießen as the centre, or one, and people can wrap the particular length of rope or string around different pegs around the country, can't they?
Yes, indeed. Yes.
Yeah.
Another example of a very difficult mathematical problem that can be presented in a simple way. The typical issue about this problem is, the question is how to go along a route. In this case, it was all the capitals of the states in Germany in the shortest way. So this is the typical problem in mathematics that comes up often. First of all, it's easy to formulate. Everybody will understand. Secondly, if it's not too many points we have to go to, it's relatively easy to solve. We turned out the 16 we have is a good number. People take typically, let's say, 15 minutes to solve it. That's just the right time so that people don't get impatient, they enjoy themselves. But at the same time, it becomes enormously complicated if you have very many points. Once you are already at 40, 50, 60 points, depends a little bit on the geometry, it becomes extremely hard to solve. It takes a long time. In principle, there are mathematical methods to do this. But again, it's a perfectly correct and non-trivial formulation of the problem. We make no simplifications, undue simplifications, perfectly correctly formulated. People understand immediately what the problem is. It's in effect also a very popular experiment. People can solve it if there are not too many points, which doesn't matter for understanding, doesn't make no difference to understand the problem. If there are 5 points or 200. Of course, too few you don't want to take because it's too easy. But then, my supervisor, when I did my degree in Cambridge, wrote methods to solve problems like this. And he always said, mathematics is a very, very universal science. You can apply it to many things. You have basic principle, but have very concrete applications. And he wrote programs to solve problems like this. And very concretely, in this country, he said, my work has applications from the rubbish collection in Reading, because it was a tour of the bands, to the landing of the moon, on the moon. Because he wrote programs also for that, solved mathematical problems which were needed to land on the moon.
Wow. Well, that is inspiring. I mean, we all know about the universality of maths and how it features in every other science, but it's lovely to hear it said once more. That's been really fascinating, Martin. And as I say to anyone listening to this, I'll put the link to Mathematicum in the description. And it's quite an easy place to get to, as I believe you've told us before. It's very close to Frankfurt.
Very close to the train station.
Yeah. So very easy to pop into and reasonably priced and run very sensibly by all accounts. I should mention before I let you go that the reason you're here at INI is because you are a program participant in the ASC program, which is Approximation, Sampling and Compression in Data Science, which is running until, I believe, the end of June.
Yeah, indeed.
So it's a pleasure to have you here, and we're so glad that you're able to share your experience of the institution which you help run. I wanted to ask you one last question, which is that have you adopted any particularly physical methods for your work with the ASC program to help you solve any of the puzzles which are being presented?
For the puzzles, not yet, but indeed these methods, which we research about at the Newton Institute, have very concrete applications in data compression. You use them, or you will use them, the new methods, almost every day on the internet. We talk about compression in particular. I'm sure you're using it at this very moment when you do this recording.
Okay, well, I look forward to seeing it in action once I start editing. Martin, it's been a pleasure to speak to you. Thank you very much for joining us, and I hope people will go on and read more about the Mathematicum and learn more about it once they finish listening to this podcast.
Thank you.
All right, bye-bye then.